In this presentation, we will study how to convert minimal pos form to canonical pos form. I have taken one example, function f, that is represented in the minimal pos form, and we want to represent this function f in canonical pos form. So let's see what are the steps involved in it. The step number 1 is finding out the number of variables and what are they. So in step 1, we have to find out how many variables are there and also their names. We have 3 variables, a, b and c. A, b and c. In step number 2, we have to find out the absent variables. So in first term, we can see that a is present, b is present and c is present in complemented form. So here all variables are present, right? And in second term, we have a in complemented form, c in normal form, but b is absent. B is absent. So simply in term 1, let's say this is term 1, we have all the variables present, a present, b present and c present. And in term 2, we have a present, b absent and c present. So this is step number 2. And in step number 3, that is the most important step, we have to retrieve this absent variable. So let's see how we can do it. And for this, I will take one example. Let's say function g is there and we have a or b and a complement or c. This is the minimal pos form because in term 1 we don't have c and in this we don't have b. So what happened to b and c in this respective terms? They must be eliminated by using the Boolean algebra, because when you write the function from the truth table, we call it canonical form, and we have all the variables present. The variables are absent in the minimal form because of the reduction by using the Boolean algebra or K-map, right? So in this I can write a, b or 0, and in this I can write a complement or c or 0. This 0 can be written as c and c complement, and this 0 can be written as b and b complement. So this is what happened to c in this first term and this is what happened to b in this second term. This is how they are eliminated by using the Boolean algebra. So we will use this logic in this problem and try to find out our solution. In first term, you have to do nothing because all the variables are present. I have taken this example because you should know that every time you don't have to do something with the terms. If all the variables are present, you have to leave it as it is. In the second term, we have a complement or c or 0, a or b or c complement, a or c, or this 0 can be written as b and b complement. And let's say this a complement or c is x. So we have a or b or c complement. Here I have x or b and b complement. If you remember the Boolean algebra, I explained you the distributive law, and in that if we had x or y and y complement, we can write it as x or y and x or y complement. So I'm going to use this law in this, and we have a or b or c complement, x or b and x or b complement. Okay, and we have a or b or c complement, and this x is nothing but a complement or c. So this is a complement or c. I am replacing this x by its actual value, or b. In this also we have a complement or c or b complement. This is the function f. This representation was minimal pos and this representation is canonical pos or standard pos, because every term, every max term is having all the variables whether in normal or complemented form. So this is clear now how to convert minimal SOP to canonical SOP and minimal pos to canonical pos. In this case, in case of pos form, we have to OR 0. We have to OR 0, whereas in case of SOP form, we have to AND 1. So this is the difference between the two forms, and rest of the things will remain same. I hope it is clear. If you have any doubt regarding this, you may ask in the comment section.